What I'm here to present is a method, several methods for construction mechanisms for habitats in space environs. So I'll cover a number of different technologies. I'll start with a brief introduction. I think we all are on the same page with our basic idea here. Then talk about some methods for isotope extraction, some habitat construction materials, a method of sweeping iron to be able to make rails on the moon, creating a railroad that allows us to get sunlight continuously on the moon, a means for being able to transport things without using fuel throughout the system or space, a method for doing station keeping without using fuel, and finally a self-sustaining system or architecture based on these interlocking principles. So what I want to present here are 4 new inventions. These have recently been granted patent status by the U.S. Patent Office. All of these rely on in-situ resource utilization, and these have the potential to allow settlement and commerce in system or space. The construction mechanisms include habitats with inherent radiation shielding, ways to make airtight structures, continuous sunlight operation, payload delivery and station keeping, and raw materials available as feedstock for doing value-added manufacturing. Why do we do this in space? First of all, our president said we should do this, so that's a good reason for me to go. I think there's a lot of other reasons as well. I'm sure you all share those same ideas as I do. Isotope extraction. Mass spectroscopy is a technique that's being used for analyzing samples. It's a very commonly used technique. These 2 inventions are based on a large-scale mass spectroscopy where you first crush or sieve the regolith to a fine granularity, vaporize it with concentrated sunlight. The surface of the sun is about 5,500 degrees centigrade, so that's the highest temperature you can get for that. But that'll vaporize just about anything. Then you can ionize this with radio frequency energy using helicon sources, pass these through a slit, and apply a transverse electric field.
Isn't regolith already very, very fine, or do you need even finer? No?
It's a range of sizes, including big rocks. So if we apply a transverse electric field by the Lorentz force law, we get a force on particles by their charge to mass ratio. So we basically make a rainbow of elements and can collect those at different locations to get the different elements. So we can get these separate elements. There's 2 configurations that are envisioned here. The first one is a zero gravity operation, where you're in a L4 position, for example, and you use a collimated beam with quadrupoles, and then be able to separate this out in a continuous operation. For a lunar operation, for a quick and dirty brute force way of doing isotope separation, we can do a radial expansion. You have a tremendous amount of loss of the material and use pulsed operation, but you can still get a reasonable amount of this material out. So the primary outputs for enabling a cislunar architecture are silicon for solar panels, aluminum for wiring, and also for welding, and oxygen, which is useful for arid oxidizers. All these have an intrinsic value, which we want to feed back into the overall economy to make it cash positive so it survives administrations. So how do we put all this stuff together? One of the things that has been assumed, this is a previous publication from Space Exploration 2005, is the vaporization yield would be about 33%. The ionization yield, including self-shielding and so forth, about 85%. So about 3/4 of what we send through this of the vaporized regolith comes out as just a slag. This slag is going to be tough stuff. It's going to be very refractory. It'll be hot. It'll be nasty. We can use the heat for a Stirling cycle to generate extra electricity power. And also, we can put a mobile workpiece into the flow of this vaporized regolith, this hot, nasty stuff, and move this in such a way that we get roughly a shape we might want for doing building. Imagine an igloo, for example. There'll need to be some shaping done on it, of course, but we can get whatever size and shape we want out of that. Then to weld this, we can use molten aluminum. One of the outputs of the separation process will be aluminum. We can put aluminum between these ceramic blocks, melt it with concentrated sunlight or with lasers or something fancier, and be able to allow that to wick by capillary action into the spaces in between and make an airtight seal. For a rotating structure, eventually we want to put a habitat in zero-G environments. So to do that, we're going to have to put tensile strength on this. So we need to have some sort of interlocking jigsaw piece. I'll leave this as an exercise for people out there to figure out how to do that. I think it'd be a tough job. The next is to extract iron from the regolith. As Dr. Jarstad pointed out, there's about 10% iron in the regolith, but about 0.1 to 0.5% of that is free iron. It usually comes alloyed with nickel, sometimes with cobalt, Sometimes it's connected in with some other silicates. But in an assumption of 0.3%, we can use a superconductor in a coil with a soft iron core to be able to suck this stuff up through the regolith. That requires us to both to lift the particle, but also to lift all the regolith that's on top of it. The regolith is about 37% porous, so most of these particles should be able to come up. For these assumptions, I assumed a half-meter depth for the regolith. In some cases it's thinner, some cases it's thicker. So here we can assume a magnetization. Here I assumed a value of 150 for chi. This is a very conservative estimate. This is the lowest you find on the Earth. I'm assuming that meteorites are going to blast magnetic domains and use a small value for that. So if we lift this particle, and this shows the size distribution of the iron particles from some earlier work, we can get most of this stuff out, about 0.3 kilograms per 0.2 meter square area with about a 4 Tesla current. That's an enormous current. So these things are going to be slammed up against the bottom of this thing. So there's a lot of engineering issues to be solved. But obviously this can be done with very easy assumptions on the superconducting wires. Next, how do we get full-time power? Well, the easy answer that everyone throws out this is put a nuclear power plant right there in the moon. All your problems are solved. I personally believe that nobody's going to let us do that. So I made the conservative assumption that we have to use sunlight. There are places on the moon's poles which may get continuous sunlight, or again, as Dr. Jarstadt said, there may be places within a couple hundred kilometers of each other that we can get perpetual sunlight with power between them. But let's go ahead and put rails around it. That way we can put trains on this thing that will have manufactories, we'll have food growing, we can have greenhouses, the people can be there, and we solve all these problems. Making rails around the poles of the moon is a really hard problem because they're badlands. This is about the nastiest place you can be. When I flew out here to Los Angeles and looked over some of the places in Utah, Nevada, and Colorado, they're bad places. But we made railroads through there back 150 years ago. So the moon nods forward and back towards us, north to south, like this, a little bit more than 6 degrees over the seasons. Because of this, I'm assuming that it's unlikely we're going to find a nice, convenient spot where we can make an expandable lunar base that'll have perpetual sunlight. So if we take that lunar libration into account and just do some simple geometry, we get about 1,200 kilometers of linear distance that's required to circle the moon so we can guarantee that we're going to get 100% sunlight. If we assume a light rail with this cross-sectional area, that requires 28 kilograms per meter of iron. To do that, we have to go from the rails 10 meters to either side with a sweeper. So the sweeper is going to cover every fifth of a square meter in about 0.9 seconds. So we're going to have to sweep out, sweep back. It's going to be a slow process. But if we have at least 2 of these, so that at least one's in sunlight at every time, at all times, then this could be done in 2.5 years. Now, that's assuming we have a straight line. So if we figure roughly double that for the circuitous path we're going to have to go on, then 5 years. But even that, 5 years is not a very long time to be able to have this great benefit. Okay, if we can launch things from the moon with electromagnetic rail launchers, that's a really great way to get things up into orbit. But then there's all this unanswered question. How do you slow this stuff down? How do you use this so it's not going to be a weapon, like is assumed in the science fiction book by Robert Heinlein, The Moon as a Harsh Mistress? So one of my inventions is a way to do this electromagnetically. Again, this is a brute force way of doing things, but it doesn't use anything from the Earth, which is the main design constraint. So we can use superconducting coils and have those aimed precisely, big control problem, but definitely solvable, to take these incoming ferrous canisters and slow them down. Now you also have to deflect them, so you can have flyby configurations, which is shown here, and pull these things into an orbit. So you're basically swooping them into a geosynchronous orbit, where they can now be assembled by robots or by people into large geosynchronous farms. This is going to cause a lot of momentum transfer between these orbiting gizmos and our payload. So we have to push these things back. So that's the other side of this problem we have to address. So that's in the next slide here. So to do the station keeping, the conventional way of doing things is ship a whole bunch of chemicals up there, hydrogen, whatever, and be able to use that for your thrusters. But these are going to be large structures, and that requires a lot of chemicals, and that's not a good answer. So what we can use is that slag that we had from the isotope separation process. We can ablate that with an electron beam or a laser beam and use the reaction force from that ablation to be able to do the station keeping. You put it out at an arm, you get a little bit of thrust, and now it's able to turn your stuff. So this may not solve all the thrust needs, but it definitely reduces the amount we need to bring to the Earth. So we'd have to shutter these lasers so they don't get blasted, so it'd be a pulse type of operation. We can configure those, like is shown here, for 6 degrees of freedom. The patent on this was granted, or was allowed last month, and will grant in July of this year. So the payload that we would ship from the moon to geosynchronous orbit would include the solar panels, of course, for collecting the power, aluminum wiring and structural materials. There's a lot of power management and distribution needs for a large solar installation, and also slag for the ablation targets. So I've got a Space Grant Consortium from Indiana, where a student is working on this to work out the energy balances for all this and find out where the sweet spot is for designing the payload canister size to be able to make all this stuff happen. So if we put this all together, what we want to do is sell power to the Earth. Because energy is one of the biggest problems facing our society at this time, if we can supply pollution-free energy to the Earth without the need for nuclear power, without the need for fossil fuels, without the need for nuclear proliferation in places like Iran and North Korea, and without causing damage to our environment from carbon dioxide emissions, we've got the solution to energy for all time. So this is the way we can do that and sell that back to the Earth. So here's where the money comes in. But in order to do that, we start off with regolith, sunlight, and then these different techniques to be able to build a self-sustaining colony on the moon where there are people who can fix the robots, operate the facilities, make sure everything works okay, and then launch things up into orbit, send them into geosynchronous solar farms, beam that back down in low-density microwaves to Wyoming. In Wyoming, they built their grid out into the middle of nowhere, assuming that somebody somewhere is going to come along and put a power plant at the end of their lines. So they're like, okay, everybody, come and build your power plants. Well, nobody's been rushing to do that. Well, they got a wasted state anyway. Let's just put some antennas down there and connect it to the grid.
Can't say that here.
Oops. A sparsely populated state.
You just got kicked off the international negotiation team.
You mentioned self-supporting
Yes.
lunar colonies. How are you going to address the need for the carbon, the nitrogen, and the hydrogen?
Those
that
are
is
huge
not
problems.
available there?
Well, you need to capture a comet, and that's going to take a long time. So until we do that, we have to methods to do ISRU, to be able to make cost-effective space solar power. The publication I had from a year and a half ago showed that we can get this down to $6 per watt, and after 5-year amortization of your initial investment, and I assumed a lower number than Dr. Frunlich assumed, of $110,000 per kilowatt hour per kilogram delivered to the moon. But it came out to the end of 5 years of 16 cents per kilowatt hour. That's lower than they pay for power here in Los Angeles. So we get living quarters with perpetual sunlight. We get entrepreneurs. We're using these raw materials for value-added work. We need factories, workers, farm workers, service personnel to serve scientists, tourists, and settlers who are going to come up here. So all of this assumes that we don't have any nice free water on the poles. All of this assumes we don't have a permanently lighted position on the moon. So if either of those two things happen, then this just gets a whole lot easier. So I think this is a neat idea that I haven't seen presented before for using synergistic methods to build habitats and bring money back into cislunar space and bootstrap ourselves to be a spacefaring society. Thank you for your attention. Any questions before Lee cuts me off?
Have you posted your paper on the web?
I wish we had more time.
Lee, will there be a proceedings published?
There will be if you send us a paper.
I did.
Have you considered not having humans present initially, using all robotic operation initially?
I think that's all way to do it.
Yeah, because there's a tremendous load up front for trying to keep people better than what robotic operations have people managing the robotic operations from a distance. So, you know, and if you lose some robots because you can't repair them, okay, you park them somewhere. You just keep going if you can.
All right, thank you all for your attention.